Welcome to the NPTEL course Computer Design of Electrical Machines. We have a lecture 2 today in which we will be covering typically with the introduction application, basic terminology, fundamental laws of electromagnetism, then magnetic materials, electrical machine constituents, and of course exercises and numerical problems followed by references. So to start with the introduction, typically of the magnetism. So application of magnetism, of course, are in electrical machines, as you can see, as a 2.2 kilowatt 3 horsepower induction motor, single phase induction, and 5 HP induction motor. Then, of course, 5 kVA diesel generator set, which normally of single phase, and then you have a 3-phase 600 kilowatt 750 kVA diesel generator set, as you can see here, where we use this typically the magnetism. And we have a large turbo generator in power plant. Then we have application of this magnetism in computer hard disk, computer magnetic tapes and floppy disk, and magnetic cassette. Then application of magnetism in the typically in moving coil loudspeaker, as you can just see. And then of course the typically lift electromagnet, which are used in number of applications. Then magnetic core assembly, magnetic resistor random memory, then the typically CRO or cathode ray tube, then the application of magnetism in nuclear magnetic resonance spectrography, then MRI, magnet resonance imaging for use for medical purpose for scanning, then the application of magnetism in magnetic levitation system used for high speed transit rail transport system, then in magnetic propulsion system, then the application of this application of magnetism in cyclotron, the application of magnetism in typically in torque mark device, then the application of magnetism in MHT generation, magnet hydrogenerator. So these are now coming to the basic terminology used in this magnetism or basics of this concept of magnetism. So magnetism is a phenomenon by which the material exert either attractive or repulsive force on another. In the typically, you can see just like a magnet that you have a flux line flows from north pole to south pole in palm magnet. Similarly, the earth is also a magnetic. So we have a magnetic source of magnetic field where you can have it is produced by a conductor carrying current, as you can see here how the flux line, or you can say the B, are around the conductor when the current flows into the conductor. Of course, it depends on the material which are around, like typical example, other example are solenoid, which used for many applications for linear motion. Then there are another like earth also, like a earth magnet, as we call it, south pole and north pole in the typically in the earth, and we have a loop, typically loop wire, where we can have a movement of the magnets, and typically by which we have typically a kind of induced EMF in the conductor line. Then of course the bar magnet, where flux line flows. So we can call it magnetic. We can define some of the typically the concept of magnetic field strength. We call it created by the current through a coil. So that magnetic field is, we call it, denote normally by H and produced by current when if number of turns in the coil are N. No, it's okay. Then we have a typically relation for the applied magnetic field H. So we have a original of magnetic moment. The magnetism arises from the magnetic moment or magnetic dipole magnetic material. When the electrons revolve around the nucleus, orbit magnet moment arises. Similar, when the electronic spin or spin magnet moment arises, then the permanent moment can arise due to the orbit magnetic moment of electron, then the spin magnetic moment of electrons, and the spin magnetic moment of nucleus. So we can call it a property, we call it magnetic permeability of this magnetic material. It is the measure of ability of material to support the formation of magnetic field within itself. And when a material is subjected to external field, material with the high permeability form a strong internal magnetic field, and material with low permeability forms a weak internal magnetic field. Then the magnetic permeability of the free space, also known as a magnetic field constant, denoted as mu0, that's equal to 4 pi into 10 power minus 7 Henry per meter. And relative magnetic permeability mu r, we call it mu r, the mu for a particular material divided by mu 0 is just like a relative permeability. Of course, you can call it like So we have here, of course, magnetic field intensity, which we already talked about. So magnetic field intensity, you can call it like typically happens. So in a magnetic field generated by passing current I through a coil length and number of turns, and then the magnetic field is strength. Well, denoted by H, that is equal to number of turns multiplied the current in the coil divided by the length of this magnetic path, and denoted by ampere per meter. So we call it magnetic flux density, which are normally used in the terminology in the design of electrical machines. So we call it magnetic flux density, the measure of lines with a medium, that is B equal to mu 0 H, and the, well, we can say mu 0 H plus M, where the mu is the, and denoted B, the unit is either Tesla or Weber per meter square, so where the mu is the permeability. So this magnetism, we normally call it typically the net magnetic dipole moment per unit volume, and it gives us the measure of the strength of a magnet, the quality of magnetism, called typically M equal to X H, which is unit is again ampere per meter. And the magnetic susceptibility, we call it like X mu r minus 1, and it's a unit select quantity, as the mu r is also unit select quantity. Like, so here we have a symbols used for this magnetism. We call it like a starting with the quantity, then SI unit and GS unit. So normally we are using now SI unit. So like a field intensity, normally we denote by H, and the unit is ampere per meter. And flux density, the unit is Tesla, and flux, the unit is Weber, and magnetization, M, we call it ampere per meter, and then susceptibility J, we already talked about, that is mu minus 1, mu r minus 1. So that's only the typically the how strength is your typically magnetic material compared to the air. Like, so coming to basic laws of magnetics, we can say the three laws. First law is the White-Savret law. So Jean-Baptiste White and Kyle Stewart discovered together the White-Savret law of magnetic statics. And White-Savret law in physics is a fundamental quantity relationship between the electric current and the magnetic field it produces. You can call it a current in a loop produces magnetic field lines B that loops around the current. And the White-Savret law expresses the partial contribution, you can call it delta B, from a small segment of conductor to a total B field of the current in the conductor for a segmental conductor of the length and orientation that carries a current is typically an example that delta B is mu 0 by divided by 4 pi into IDL into sin theta upon R square. So that's a small incremental, you can call it the field. Like, then there is another law which is called Gauss law. The total electric flux passing through any closed imaginary surface and causing the charge Q is equal to the, you can call it Qn, and the total flux phi E is the equal to the phi, the surface integral of d phi, and that's a ds equal to Qm, and where the ds is the electric field intensity. So now we have, of course, the typical law of the left hand and right hand rules. So in left hand rules, we say that you get typically when you have a motion, and you can call it, you apply a field, then you have a current here. So this is responsible by typically a field and current give you a torque which, or the force which give the motion, normally used for the motor. And the another is that if you have a motion and you really apply the field, then you get the induced EMF, that normally we use in case of typically in the generator. As you can typically in the two cases, you can say df IDL into B, and or F equal to, you can call it BIL. So where the B is the flux density, I is the current, and L is the length of the conductor. Like, so right hand rule shows the direction of induced EMF, and you can call it D is equal to V into BDL and E equal to BLV. That's the induced EMF in the conductor, where B is the flux density, L is the length of the conductor in the active portion where the flux lines are moving, and V the velocity of the conductor. Well, there are, of course, law of magnetics by engineering effect of magnetic field and electric current, and there were three natural philosophers who did more than any other to get the engineers started in their explosion of the phenomena, and they were Strad, Amperes, and Faraday, and their most important work was done between 1820 and 1831. So now, typically background of Faraday law is a coil of the copper which is stationary, the magnetic field of varying intensity has a voltage induced in it, and this we call it the stationary induced EMF, or we call it transformer action, because here the conductor is typically stationary but field is moving, or field have a variation with respect to time. So another is the coil is moving relative magnetic field of the field intensity, and also have induced EMF in it, and this we call it generator action, or we call it like a speed voltage or motional voltage. And normally, I mean, this is typically what we have in case of the DC generator or many electromagnetic machines like that. So the another typically Faraday law and flux for the flux is the induced EMF in a proportional to the number of turns on the coil, and is also proportional to the rate change of what we call it magnetic flux phi, and we call it induced EMF is n d phi upon dt, because of the rate change of the flux. And since F equal to BIL, so solving for the flux we call it phi equal to 1 upon n E theta plus cos a constant, integration constant, and where phi is equal to B into dA, that's a BA. So flux is a flux density multiplied the area. So net flux flowing into this is flood. I mean, typically this flux density, and it's how much area it is flowing through it, that we get the total flux. So typically this law of the flux goes virtually in this way: when the magnet is moved towards the stationary conductor, a current is induced in the direction shown in the, and the magnetic flux line are due to the bar magnet. We consider why current will flowing, it's a closed conductor path. And in case of the second, we call it the induced EMF. Induced current produces its magnetic field direction to left counter to increase the actional flux like that. So when the magnet is move away from the stationary conducting, a current induced in the direction as shown. So direction changes accordingly, and the induced current produces a magnetic field direction to the right, so the counteract the decreasing the flux line. So coming to another law which called Ampere law. So background of this Ampere law, although Faraday discoveries give us a precise way of quantifying the flux and flux density, they cannot be used for engineering design and analysis unless one can conclude phi and B by some other independent method. So for example, one cannot predict the induced EMF in a coil unless one already knows the rate change of the flux linking in it. So coming to typically Ampere law and field strength, on which the field strength really based, Ampere law says that there is a magnetizing force or magnetic strength and circle any current, or and that the integrated value of the H around the closed contours surrounding the current is equal to the current itself, right? So we can call it line integral H into ds equal to I, or total typically MF. Solving the field strength for a closed contour radius, we call it ds equal to H into 2 pi a, and that's equal to Ni, the total MF applied to produce this field line. And therefore H will be Ni upon 2 pi a, where the 2 pi a is the typically, you can call it the periphery of the typically of this field line. So now coming to relationship between B and H. So it's necessary to describe the magnetic problem using both parameter B and H. And why the B obeys Faraday's law, though through B phi equal to BA, H does not, and H obeys the Ampere law, B does not. So to solve any electromagnetic problem, one must relate both Ampere's and Faraday laws, and this is done using the material property mu as a permeability. And you can see just example here as a material property. We can call it a magnetization characteristic of a material where flux density is on y-axis and x-axis we have a magnetic field strength H. So you can just see this curve. Typically, if it is typically a linear material like air gap, we have a linear characteristic, it does not saturate. But when we have a typically a ferromagnetic material like a soft magnetic material or so, then you can just see there is after a certain strength of the field, it's automatically showing the kind of saturation properties. And in saturation property, of course, we define the characteristic in these two manner. One is the apparent, you can call it permeability, that is mu upon H for particular point, and then we have incremental probability, we call it dB upon dH. So by which, of course, we can really analyze the machines even with the some level of the saturation, which is normally there in the. So how really we take care of this saturation also into account while designing the machine or otherwise. And of course, you can just see this characteristic for different kind of material. You can see for ferromagnetic material there is a saturation, but if you talk about paramagnetic material, superconductor type material, vacuum and diamagnetic material, of course it does not show any kind of level of saturation like also. Now coming to another law of magnetics, the famous Maxwell equation based on which total finite element analysis is really it goes to very basic concept of this magnetic field or calculations. So the Maxwell have developed these equations. So Maxwell equations are a set of partial differential equations that take a very precise analysis of piecewise, or you can call it the it's a distributed parameter approach we use for analyzing the electrical machines, and there we use this Maxwell equation. So used to explain nature of working of magnetic and electric field, and Maxwell four equations have been derived like Gauss law of electricity, Ampere law of current in a conductor, Farad law of electromagnetic induction, Gauss law of magnetism. So these are the four laws which really put into Maxwell equation form. And Gauss law of electricity defines the link between the static electric field and the electric charges that generate the electric field. With the first law, and Gauss law of magnetism that states the net magnetic field and passes through the closed surface of is zero. I mean that's a line integral is zero. And Faraday law of induction states that the magnetic field generated around the closed loop is equal to the work done in a to move a unit charge within the loop. And Ampere circuit law says that a magnetic field can be generated by the electric current by changing the electric field line. So Maxwell four equations are based on the concept of how the magnetic field or electric field are generated by current, charge and change of the field. And these are the typical Maxwell equations starting from first from basic principle involving the Gauss law or inverse field of monopoles as a line integral of the typically that is a your charge upon permeability, and then you can see the final equation of differential equation form. Second Maxwell law is the virtually typically Maxwell equation is a Gauss law in line integral that's typically over the you can close path is your B into D equal to 0. And the third Maxwell equation is the Faraday law of changing magnetic field strength, that's a E into dl that is minus d upon dt B into A, on which the induced EMF really concept is applicable, and the Maxwell. But all these equations are only applicable for, you can call it very small element or partial derivative only. A Maxwell equation for Ampere Maxwell magnetic field equal to B delta equal to mu 0 I plus mu 0 I into delta. So that these are the four Maxwell equations which are quite popular to analyzing the basic concept of this electrical machines like So you can call it magnetic field of current carrying wire. It is experimentally observed that the parallel wires exert forces on each when the current flows, and you can say when two parallel conductors typically have a carrying two currents in the same direction, they have a force of attraction that is shown in the symbol by blue line, and when the two conductors shows in opposite direction, they have a current opposite direction, the force is a kind of repulsive or opposite direction like. So you can call it the magnetic field in a current carrying wires. The force on conductor 1 due to second conductor magnetic field is, you can call it, follow the basic law of right hand, you can call F1 2 will be I1 L1 into B2, and B2 equal to mu 0 I2 2 pi d into K, and then F1 2 you can put the value I1 L into J into mu 0 I2 upon 2 pi d K, and F1 2 if you really put all value mu 0 I1 I2 L upon 2 pi d into typically unit as a vector I. So this is typically you can call it the force there when two parallel carrying conductors are there like and it becomes very relevant in many cases when under normal condition force may not be too much high, but when there is a very large excessive current because of some fault or some operating conditions, like in a very large generator, say turbo generator, if there is a short circuit, then very large forces are produced, and to take care against that we have to really put the winding with the proper strength. So the force per unit length of wire is F12 on L mu 0 and I1 upon I2 into 2 pi d as a typically direction of the field I. So similarly, magnetic field of current carrying conduct wire, the force on the conductor 1 due to conductor magnetic field F21 I2 L2 V1, and B1 where is minus mu 0 I1 2 pi d, because and then F21 is again you can express finally the force F21 that is minus mu 0 I1 I2 L upon 2 pi d, and the force per unit wire is F21 upon L minus pi 0 I1 I2 upon 2 pi d into I like. So that's really the force per unit length of the conductor like. And finally we use typically the concept of here how the if a one carrying conductor produces the field and another carrying conductor experiences the force on it like due to another. Similarly, magnetic field of carrying conductors when they are in opposite direction, similarly you can derive the relation for typically the forces. So magnetic field of a carrying conductor, if current in the wires are the same direction, the force is attractive. Current in the wire's opposite direction, the force is repulsive, and magnitude of the force is F1 equal to F21 mu 0 I1 I2 L upon 2 pi d, and you can just keep the value of even so F1 2 equal to F21 4 into 10 power minus 7 I1 I2 L upon 2 pi d, and that goes to 2 into 10 power minus I1 I2 upon L upon d. Now coming to electric and magnetic force, the magnetic field exerts a force on the moving charges, and the force on magnetic field exert on a charge on q moving the velocity v, called the magnetic Lorentz law, is given by F equal to q v into b, where q is the charge, v the velocity, b is the flux density, and this Fa you can just put the value of typically q v b into sine theta. I mean, if angle is there between the two theta, like theta is the smallest angle between the direction of the vectors v and b. So the force F is perpendicular to the direction of the magnetic field B. It is also perpendicular to the direction of the velocity, and F is perpendicular to the plane that contains both V and B. So if the charge is moving with uniform velocity V parallel to the direction of the magnetic field, it experiences no force. It continues to move with uniform velocity along with the line parallel to the field, and typically the force on a straight section of wire in a uniform field is F equal to IL into B, and you can call it F equal to BIL into sine theta, where theta is the smallest angle between the direction of vector L and B. Well, we have another law of Lorentz force. So Lorentz force is the force exerted on a charged particle in moving with a velocity v through an electric field E and magnetic field B. The entire magnetic force on the charged particle is called Lorentz force and is given F equal to QV plus QVB. And the first term is contributed by electric field, and the second term is magnetic force that has a direction perpendicular to velocity and magnetic field. Now coming to the materials, first we would like to talk about magnetic material. So type of magnetism, I mean, in this magnetic material, the material is magnetically characterized based on the way it can be magnetized, and this depends on the material magnetic susceptibility, magnitude and sign. And there are three basic magnetism: diamagnetism, paramagnetism, and ferromagnetism. And in ferromagnetism also there is anti-ferromagnetism and ferrimagnetism. So coming to typically the classification with the founded dipole. So we have a diamagnetic material when typically they are not lying, and when there is a para, ferro, and anti-ferrimagnetism like. Then alignment of dipoles, if it is there, then with the random it is a paramagnetic. If it is a uniform, we call it ferro or anti-ferri magnetics. And then direction of dipole, if it is in the same, then we call it ferromagnetic. If it is opposite, then we call it anti-ferri or ferromagnetic. Like, so then the magnitude of dipole, it also goes with the same direction than ferromagnetic, and if it is different, then we call it ferromagnetic. So these are classification of typically of magnetic materials. Like, so these ferromagnetic material, which are much used in electromagnetic machines, these are materials in which the magnetic dipole interact in such a manner that they tend to line up in parallel. And ferromagnetic substance consists of number of regions or domains which are spontaneously magnetized, and the direction of magnetization varies from domain to domain. The resultant magnetic is zero or nearly zero, and the relative permeability is very high. In presence of external magnetic field, the ferromagnetic material get strongly magnetized and exhibit hysteresis loop. And above the purity temperature, the ferromagnetic material exhibit the ferromagnetic behavior. And the ferromagnetic materials are widely used in industry. Typical examples are iron, nickel, and cobalt. And this ferromagnetic material, typically you can just see how really the magnetic field produces it. I mean, here that, I mean, in different type, if we can call it applied magnetic force is there, then there is a alignment. If there is no field aligned, they are not aligned. And here comparative analysis, you can say in magnetic material under H0, you can just see that they are not really typically magnetized a diagnetic material, and of course with this they are oppositely, you can call it aligned. And in paramagnetic, of course they are randomly aligned if there is no magnetic field, but magnetic field if they are aligned in a direction of magnetic field. You can just see with the how the orientation in ferromagnetic value, ferrimagnetic and anti-ferromagnetic is there without, you can call it the without field applying and with the field applying. Like, so now you can say the magnetization characteristic which is we call B versus H of magnetic material. You can just see in a ferromagnetic material where relative permeability is more than air permeability. I mean, like you can say all are typically kind of aligned, and in ferromagnetic they are typically aligned typically in opposite direction, and paramagnetic material they are not aligned randomly, and typically vacuum or diamagnetic they are randomly aligned with magnetic field. So this is typically the property of this characteristic of this different materials, I mean, which we can classify in these category either ferromagnetic, ferrimagnetic, paramagnetic or diamagnetic. So this typically again the comparative analysis of this different materials, typically of diamagnetic material where we have a different material similar to like a copper, how they really behave, then paramagnetic like aluminum and typically, and then ferromagnetic in ferromagnetic material which they are aligned with them magnetic, and we have a property similarly what we call magnetization characteristic. Then antiferromagnetic where very low, I mean, field is applied, and ferrimagnetism here you can just see how they are aligned and they show the characteristic magnetization characteristic of the material like. So now coming to BH curve and hysteresis loop of ferromagnetic material. So you say typically we have a domain structure and the hysteresis loop. So according to the Becker's law, there are two independent processes which take place and lead to magnetization when magnetic field is applied. So first is the domain wall moment on domain strength, and second is the domain rotation. And domain wall moment or domain wall growth, volume of favorably oriented domains will increase, and it occurs at low magnetic field, and it is a reversible process. So each domain is magnetized at different direction, and applying the field changes the domain structure, and domains with magnetization in direction of field grow, and other domains shrink. Like as you can see, example unmagnetized, and then you can say magnetized. How the typically the domain move with the magnetized conditions. Like. So now coming to rotation of domains, the rotation of less favorably oriented domains take place and occurs as large magnetic field. It's a irreversible process, and finally by applying a very strong field can saturate magnetization by creating single domain. So you can just see how it is unmagnetized with the field and how it is with the magnetized typically in domain direction, and then applying very strong field can saturate the magnetization by creating a single domain. And you can just see how this typically a domain structure of this hysteresis loop under ferromagnetic or ferrimagnetic typically material initially unmagnetized, as you can see in the top of ferromagnetic, and domain construction with several stages of magnetization and saturation, flux density, magnetization, and initial probability, as you can see for different kind of material like. So now coming to hysteresis loop, the loop traced by magnetization in a ferromagnetic or ferrimagnetic material such as magnetic field is cycled. So loop is known as hysteresis loop or BH plot or MH plot. So you can just see how this is. We can have a typically a core, you can toroidal core, and we can have a certainly the winding on it, and we can excite with the DC by switching, and with the different we can change the different current into it. Starting from typically we apply the field from 0 as you see the blue line, and then you can reduce it. It does not come to 0, it goes, and then you can apply opposite direction and come to. So it produces the typically a loop, and this loop we call it the hysteresis loop. And of course is termed as a kind of the losses in ferromagnetic material when the alternating field is applied typically on a ferromagnetic material. So removing the field does not necessarily return the domain structure to original, as here we call it magnetic hysteresis. And we come to back at it explained in the previous diagram also and here also, and then you have to apply the typically a negative field which you call it coercivity SC. And here you can have a different terminology at typically we can call it at point A. I mean, you can just see we call it initially, I mean, the different points we identify here. So we call it point A, the B maximum, the first point on the characteristic and saturation magnetic field density. Point B, which comes on typically on the residual, we call it remanent magnetism or flux density, and we point C, we call it the coercive force, the field needed to bring the magnetization back to 0. And then of course it repeats like. So ferromagnetic, the magnetic hysteresis, if the magnetic current in the coil is reduced to 0, the magnetic field as circulating around the core can also reduces to 0. However, the magnetic field flux density does not reach 0 due to the residual magnetism present within the core, and it is equal to remanent magnetic flux density Br, also called retentivity. To reduce the flux density at point Br to 0, it is necessary to reverse the current in the coil, and magnetic field intensity which must be applied to null. The residual flux density is called coercive force. So now coming to the materials, I mean typically ferromagnetic material, we have a hard and soft magnetic material. So the types of magnetic material, we call it soft magnetic and hard magnetic material. So if we say for soft magnetic material, these are easily magnetized and demagnetized, and it has a high, you can call it initial permeability, as you can see in the diagram. It has a low coercivity, so that you can completely magnetize with a small magnetizing opposite force, and reaches to saturation magnetization with a relatively low magnetic field. So it has a very small size of the BH loop, and certainly you have a very less losses as well as core losses as a loop hysteresis loss in this, as well as you does not require very large excitation if you are using this such soft magnetic metal. That's the reason we use this soft magnetic ferromagnetic material in the most of the electrical machines. So it can be easily magnetized and demagnetized, and has a low hysteresis loss. It has a low magnetic friction. It has a high saturation magnetization, and application involve generator, motors, dynamos, cores of transformers and switching circuit. Now, importance of soft magnetic material is the saturation magnetization can be changed by alternating composition of material. An example is substitution of Ni square is in place of ferrite. Square changes saturation magnetic for ferrite, and susceptibility and coercivity, which are also influence the shape of hysteresis curve, are sensitive to the structural variable rather than composition. So low value of coercivity correspond to the easy movement of domain walls, and magnetic field changes magnitude and the direction. So the commercially used soft ferromagnetic material, or some of the ferromagnetic material employed in commercial practice, may be considered on the following three classification: solid core, electrical steel and strip, and special purpose alloy. So solid core materials are like, typically these materials are normally used for parts of magnetic circuit carrying steady flux, such as cores of DC electric magnet, relay and field frames of DC machine, typically iron, low carbon and silicon steel, cast iron, grey cast iron, cast steel, soft steel, and ferrocobalt. And CT steels present the laminations used in electrical machines and in transformer working at nearly supply frequency are made silicon steel, in which the content of silicon lies from 0.3% to 4.5% by the weight, and cold rolled guaranteed steel is suitable for the use in transformer, also in large servo generator. So special purpose alloys typically are in order to find high flux density in weak magnetic field. Say instrument transformer used in is made of special magnetic alloy having a high initial and magnetic permeability, and important alloys in this category are momental, contains certain amount of copper; permoil contains certain amount of nickel; superalloy contains iron and nickel alloy with the copper; and permeor alloying of nickel and iron and cobalt; and permeor contains cobalt, vanadium and iron. So these are typical applications of these soft magnetic materials. So starting if frequency is typically static less than 1 Hz, is the soft material like typically permeor and or permalloy used in electromagnetic and relays, and low frequency 1 Hz to 1 kilohertz, that's used very wide range typically of most of the our electromagnetic machine, SI steel permalloy filament used in transformer, motor and generator, and outdoor frequency like 100 Hz to 100 kilohertz permalloy foils, filament magnetic glasses like FESI, Allen powders, imaging. So it's used in inductor transformer for switch mode power supply, TV flyback transformer, and radio frequency 0.1 to 1000 megahertz. Basically use magnesium and zinc ferrite, and use inductor antenna rods, and for microwave less than 1 gigahertz, which are 5G ferrite, and they use microwave isolator, circulator, and phase shifter and filter. So typical examples of application are electromagnetic relays of these soft magnetic material and electromagnets. Then typically in inductor of different sizes and different frequencies, then use the E-type core in the typically inductor and transformer, and then this RM type of core, then EQ type of core, and then applications of course antenna rods like, and another TV flyback transformers we use for high frequency, then phase shifter, then typically the filter, EMI filters used normally in the most of the power applications on the power side. So we have a characteristic of hard magnetic material with a low initial permeability and high coercive and high remanence, and size of the BH curve is also large, and high saturation flux density, and reaches to saturation magnetization with high applied magnetic field, and it cannot be easily magnetized or demagnetized. So it's a high hysteresis loss. So we call it these or it means it consists of a large area of the hysteresis lobe, and normally used as a permanent in the most of the applications like. And typical examples are used in fractional horsepower motors, or it is used hard magnet in automobile, uh, or it is used typically in audio and video recorders, as you can just see with the different examples. And then earphone, computer disk, then magnetic clock. So there are comparison of hard and soft magnetic material. So soft are have a low hysteresis loss, and hard material have a large hysteresis loss. That's why we don't use with the AC excitation. We consider this a permanent, only give a one kind of the typically the field. And soft material have a domain wall moment relatively easily. Domain wall moment in hard material is difficult, and we have a coercive and retentive is small. And in case of hard magnetic material, coercivity and retentivity is large as in permanent. And typically in soft material can easily be magnetized, demagnetized, but hard magnetic material cannot be easily demagnetized and demagnetized. And the soft magnetic material magnetostatic energy is small, and in case of hard magnetic material, magnetostatic energy is large. So these are further some additional features of comparison. Soft material have a large value of susceptibility and permeability, and hard material have a small value of permeability and susceptibility. Soft material used as electromagnet, and hard magnet used as a permanent. And soft material core of electromagnet, electric motor, transformer, generator, and other electrical equipment. And hard magnetic material used in typically as a magnets in fractional power motor, automobile, audio video recorders, or earphone, computers, and clock. And soft magnetic material have a low carbon steel, silicon iron, superalloy, and permalloy, and ferrite. Here the hard magnetic material is typically cobalt steel, tungsten steel, silicon cobalt, medium iron boron, and cufine, and alnico. These are permanent material. Virtually we call it hard magnetic. So coming to typically the different constraint of electrical machines, or you can call it part or components. So we can call it the required material for motor and generator consists of coal and stamping material of soft ferromagnetic material like in stator and rotor. Permanent material also we use in stator, depends on which machine. If we are using a permanent brush DC machine, the permanent are put on the stator, and if we are using a permanent brushless machine, either PMLDC, or we are using a permanent synchronous motor or generator, we put the permanent in the rotor. So now in brushless machine, the permanent are put in the rotor. Then the conducting material we use normally for electrical circuit like called winding, and of course we use the insulating material, which are typically a kind of a insulation or guard on the wires, typically made of either paper or the chemicals, or typically organic materials like and mica insulation and other things which are used in the machine. So of course it use very less area, and design of depends on mainly on the quality of material used. And if low quality materials are used, the machine will be less efficient, more bulky, and higher weight and higher cost, and operating running cost will be also higher. And designers should have perfect knowledge of property and cost of these materials so that the design can be both efficient and cost effective. So typically coming to the stator of most common constructions of with the concentrated winding, as you can see it here in some of the machine, and of course some of machine we have a distributed winding. The typical example of distributed winding is your induction motor stator and synchronous motor stator, or as well as permanent synchronous motor of stator and other machines. And of course the concentrated winding you can see on the permanent, you can call it of the rotor of cylinder pole synchronous machine, as well as typically the DC machine on the stator. Like so, another is two pole winding with construction how we look at a field pole, and consider winding on the typically segmented stator construction, and typically the slotless winding for using so very small motors for with the typically the winding is also concentrated, but typically have another kind of construction like in axial field machine. So we have another common construction of the winding like PCB winding, as you can see here, and then we have a copper bar winding in some of the machines, then slotless air gap windings typically in case of axial field machines. Like so, here you can just see how the rotor construction is there. In induction motor, we have a rotor construction typically smooth with the cage bars, and then surface mounted permanent. We have a magnet on the surface, or we have interior permanent in the buried into the rotor in ferromagnetic material. Like. And then we have a synchronous generator wound field on the rotor for the DC excitation with the silent pole construction considered winding. And we have of course the permanent on the rotor, and with the typically Hall-back array with the flux barrier and with the permanent on the rotor. You can see the typically stampings of the stator and rotor with the lamination steel and the stack of laminated steels, like how these laminations are stacked to form the complete stator. Then we have a winding, typically the winding conductors by which we make the winding, and from making the after winding we put a rectangular conductor, typically in case of the winding some specific winding of low voltage, high current, and then we have a rotary stack winding, typical example here with the providing the field excitation. Then we have a permanent for permanent motors. It may be for permanent brushed DC motor or servo motor, or it can be permanent brushed DC motor where we put the magnets in the rotor. And of course, tubing of the permanent rotors to specific for different sizes and different kind of the rotors like and then you can just see how slot paper insulation is put into the slots of the stator laminated structure like also. And then of course you have insulation varnish, on typically putting on this, and then you have enamel copper wire which is also having insulation over it, which is used for purpose of winding. Then we have a core stamping material. So active magnetic material used in electrical machines. All electrical machines types require soft pure iron material to carry magnetic flux around the circuit, and impurities like carbon contribute to hysteresis losses, and high flux density and frequency contribute to eddy current losses. All electrical machines require conductors of electricity, and copper has lowest electrical resistance, and permanganate are considered magnetic materials, and base grade exhibit high hysteresis residual. So electrical steel, which we have a soft iron used for rotor and stator core from sintered electrical steel grade, and can be used for complicated core shapes, and rotor stator core laminations for punch from electrical steel laminations grades with low core loss and surface insulation, and non-oriented steel, typical example with the grade of M19 grades or grade 24, 26 or 29 gauges are available, and oriented M3 grades with the typically of 0.03 inch thick laminations and stator core component from amorphous material like metal glass, and lowest core losses with the fabrication difficulties like so medium to low flux density with typical example is 1.5 Tesla maximum, and both Fe and CO ferromagnetic and cobalt based alloys are also used. So typical examples are here of soft sintered ferromagnetic material which is really used, and here you can see the property here, typical property of iron, silicon iron or phosphor iron or iron nickel of different kind of material with the different properties here of silicon steel. So typical example here how the BH curve for different somo alloy or typically of laminated structure of 0.35 thickness silicon steel laminations, and powered soft iron, typically magnetic materials. Homo iron coated magnetic powders with the insulating layers and compact into complex shapes used in electric motor stator and rotor component. And here we have electrical steel sheet as standard dimensions, as you can see in the photograph. It's a ready-made punch steel sheets are available, and with the insulation coating to reduce the typically your eddy current losses, and then modify magnetic characteristic around the steel sheet, which we call it guaranteed and non-guaranteed steel sheets. And of course, these we use electrical laminations used in low frequency 50 to 500 Hertz. Typically in transformer and inductor, and easy to manufacture and see. And of course, silicon steel added silicon increase the resistance, reduce the eddy current losses in the typically in the steel sheet like. So the grades are called out in increasing order of the core loss by M numbers, so such as M19, M27, M36 and or M43, with each grade specifying a maximum core loss, and insulation on these we call it C0, C3 or C4 or C5. So these are typically the property how we really put. Then of course cold roll laminations is still called CRLA, and you can see the laminations typically used for induction transformer. Carbon steel should be considered for applications where the relative high core losses are acceptable, like in DC pole fuses, low duty cycle, and the first cost of the end units is of the primary importance and having a lowest cost and higher core losses. So we have a nickel steel normally used for high cost than the silicon steel and high permeability and low core losses, and lower saturation limit of 0.8 Tesla to order of that, and two alloys of 49% nickel and 80% nickel iron, with the balance being primarily pure iron in both cases. And you can say the cobalt steel we use in some of the machines lamination. So cobalt steel trade name is a Hyperco or vanadium permedia. Laminations are necessary in certain applications, but due to their very high cost, must be considered a last resort after examining the other alternative, and have a high saturation flux density order of 2.2 Tesla. So certainly will be able to reduce the size of the machine. So use very specific high efficiency, typically machines like, and high saturation flux density of 2.2 Tesla, and suitable for mass critical applications like aerospace and military applications, where weight and volume are the very prime importance. So we want to reduce the size of the machine and weight typically like. So there we use this kind of lamination. And this cobalt steel and silicon steel, how this characteristic of your frequency versus typically the core loss, I mean that is core loss in watt per kg, produced just as a characteristic of the these materials like. Then we have a other materials, we call it like a typically ferrite cores, sintered iron oxide, magnetized zinc, and low saturation flux density with 0.4 to 0.5 Tesla, and they are brittle like ferrite cores. Of course, they are used in high, have a high permeability order of around order of 3000, and used in choke and filter typically in many applications for inductor as well as high frequency transformers like. Then we have a typically steel AISI or ASI steel numbering. Example is AISI number 1020. So first digit indicates that this is plain carbon steel, and second digit indicates there is no alloy element, and the last two digits indicate the steel contains approximately 0.2% carbon. An example second is ASI is the 4340. The first two digits indicates the nickel chromium alloy steel, and the last two digits indicate carbon content really roughly 0.2%. So with based on those nomenclature, you can see different grades of the different kind of steels here, and you can just see the material property of, I mean, of different kind of materials like of these steel laminations also. Similarly, we have a steel of for use for different applications, for rotary, large rotating machine, medium rotating machine, and hermetical machines, and typically for static machines like transformer of different type by JFE steel laminations from Japan. Then we have a JG cores used for different applications again at different frequencies, as you see with the maximum flux density order of that, and with the density of this ferromagnetic material like. So these are the property of different kind of grade steels coming from different country like from Japan also for use for different applications like. Then typical example of again the non-integrated steel strip, the property of the different steel, and it's used for different applications like their mechanical properties also. And then data sheet for electrical steels. I mean, you can just see thickness, maximum loss, specific loss, typically the core loss at different flux density, and minimum polarization flux density and convention density. So you can see the property of different silicon, typically steel used in for core or as a ferromagnetic material in different machines like also. So now coming to typically a material used in different parts of the motor or stator, as you can see here the cell and pole synchronous machines for low speed. So we have here the typically the laminated non-insulated steel with the laminations of 2.5 millimeter used in cell and pole synchronous machine. The solid steel bag typically of the body of the pole, and then we have a coil on this concentrated coil on that, and we have on stator again the typically the coils in stator slots with the laminations of 0.5 mm on stator, because that's normally the 50 hertz or 60 hertz excitation. On the rotor, we have of course the DC current flowing into the winding like of this, typically of large alternator of low speed like water wheel generator, or typically sometime in case of even the diesel engine generator sets like. So coming to losses in electrical steel, so you can call it there is a typically iron loss. So losses generated in iron core partially parts such as stator yoke and stator teeth are caused by changing magnetic field, and total iron loss are composed of two loss components, hysteresis loss and eddy current loss. And here you can say calculation of hysteresis loss, what we call it in watts by analytical method. Modeling methods such as parasitic, Hastron and curling are used to hysteresis loss calculation or prediction. We find out the area of the loop, and then from this we calculate how many times this what the frequency is, that from that we multiply it and to get the total losses in this. So hysteresis losses are equal to the area of inside the BS loop started when material is subjected to magnetization, saturation, and complete demagnetization, or we apply the alternating field to across this. So this hysteresis loss, you can call it are calculated by analytical methods. WH equal to CH B to power 1.6 peak flux density as shown here, and F into M. So where F is the frequency, M is the mass of the core in which we are calculating typically the core loss. C is the Stimmons constant as a property of the material used here, and B the typically the maximum flux density, and F is the excitation frequency. Similarly, we have eddy current loss. Analytically, we calculate again the a reasonable analytical formula is V square peak flux density square F square T square, that is the thickness of the laminations, and pi square and sigma, and CPM where M, where again the F is the frequency, M is the mass of the core, C is the estimate constant, and C T is the lamination thickness, and delta is the lamination conductivity, and rho is the density. So it's used for calculating the sum of parts of the hysteresis laminations multiply the watt per kg and cause losses. Typically depends on the flux. So where the one flux density there, we calculate the typically, and if it is another part, we have another flux density, we calculate from similarly for that kind of volume and weight. So here is a how you can separate the eddy current, the hysteresis losses, because one loss if you take with the empirically is proportional to frequency, another is proportional to frequency square. You can measure these losses at two different frequency and get these typically, and you can separate out these two constant, you can get it by conducting actual experiment on the existing machines to divide this. So now coming to typically on permanent, which are really having a today large importance in typically of different kind of machines, especially even a rotating machine as well as the stationary machines. So you can say here how we define, if we have a typically BS curve of a magnet is desired large retentivity, remnant flux density should be large, as you can see second characteristic, and large coercive force. So we can consider the hard ferromagnetic material with large area where the residual flux density is also large, and your typically you can call it coercive also large. We consider a good permanent material, and when we have a typically low this, so we call it like it's a not a that good permanent material as a soft magnetic material. But of course, we have a characteristic where we have a large residual flux density but low coercive area, or we have a low flux density, large coercive area like in a ferrite. Of course, we have a permanent which have a large coercive force as well as large flux, residual flux density. And typical examples you can say here of different kind of permanent material, how they are really with the different number of magnets, orientation of different kind of radial oriented, diameter oriented, and used in really in different kinds of machines in magnetization with the proper magnetization direction. So classification of permanent material is there are three classes of permanent material currently used in electrical machines. That is alnico, consists of aluminum, nickel, cobalt, and iron. That's alloy, and ceramic, that's called ferrite, that is barium ferrite and stone ferrite, and then rare material like same cobalt and neodymium iron boron. So these are three basic classification, and there you can call it energy density. That's a you can call it the energy density produced, like it's a typically how much field they can have in particular volume. They can store the energy, that called energy density. It varies over a wide range. Like as you can see here, we call it maximum energy product, BH maximum, with the typically how it is developed energy density over the years from 1915 to typically coming to of 2020. So here you can just see how really it goes into the steel, then how going to ferrite, how it is going to typically in alnico, how it is going to typically ceramic cobalt, and how it is going to neodymium iron boron. So you can just see after around typically of neodymium iron boron start coming of 1995, it has gone big way, and you can see the energy density of this neodymium iron boron is typically around maybe you can say around 10 times or 8 to 10 times more than what you have in case of ferrite. Also, or even typically around 6 times, around 5 to 6 times with the typically with the alnico. So that's the reason nowadays we in good machines we start using neodymium iron boron, that is reduces the size of the machines. So these are typically how the property, or you can call it the energy maximum energy product, which is responsible for deciding the size of the machines and how much energy you can store in a particular volume of the machine. So you can just see even the BH curve in the second quadrant, which is more responsible, which really talk about the residual flux density as well as the coercive force. I mean, what we define in BH curve. You can just see how much it typically we design virtually at the maximum area of this. So you can call it half BH will be the typically. So you can find radium and boron compared to ferrite. I mean, you may find this area maybe probably around 10 times, and then followed by sodium cobalt, then followed by typically alnico and ferrite. So these material alnico and ferrite saturates very low flux density around 5.4 Tesla, and you design the machine around 0.5, 0.2 or 0.25 Tesla only. I mean, and typically similarly alnico also you design at, of course, little higher flux density, but the coercive force is quite small. Sodium cobalt have an advantage that temperature coefficient is very low. Of course, neodymium iron boron have an advantage that energy density is very high, but the problem is temperature. I mean, the property changes with the temperature, but that now new alloy, I mean, this, I mean, problem is also taken care of. So we start using now, of course, neodymium iron boron, and lot of compounds of neodymium iron boron have already appeared. So you can say how it is look like. Typically, classification of permanent material, size comparison for permanent material producing the flux density of 0.1 Tesla for distance of 5 millimeter from the face. So you can see the size, how it is ferrite, then alnico, sodium cobalt, and indium iron boron. So if you can just see, you require so much area of 25 centimeter cube, then you require 0.3 centimeter cube only as a you can call it the typically volume required for same flux density produce. Like, so you can just see it's a almost like a 1/10, one typically in less than 1/100th order of inch cobalt compared to ferrite. Like, so you can just see the classification of this permanent, how really goes with the typically coercive force and flux density, this residual flux density, how it has gone the neodymium or boron compared to your typically ferrite or other product. I mean, like, so that decide the property of the material to be used in different machine. And here you can see the here how the prices also changes. Like, I mean, that's the reason the price of your typically of neodymium cobalt is quite high, but of course we are using neodymium iron boron reasonably, but the price is also too not high, too much is not so high, but energy density is quite high, as you can see from the first column as well as the other property of this permanent material. Now coming to classification of permanent material, starting with the alnico. The developed alnico began in 1931, and alnico magnets are made primarily from aluminum, nickel, cobalt, copper, ferrite, and titanium, and they can either be cast or sintered. Various type of alnico differ not only by the composition but also by heat treatment, and you can see how the alnico cores are available of different permanent kind of material for different applications, and then different grades of alnico with a different residual flux density and coercive force, and what is the energy density. Typically you can call it BH max, like, I mean, here in different alloy, but of course it does not, it's hardly touch around like 83 or 84, not more than that. Then we come to different, you can call it composition, how it look like. I mean, the brands available for alnico of alloy, and then how we use the alnico magnets in the motors, usually an application where high operating temperature are there, and application are electric motor, microphone, sensors, aerospace, and military application. Then we have a ferrite magnet that are very extensively also used now. Ferrite magnets are ceramic magnets are produced calculating between 1000 to 30 mixture of iron oxide and strontium carbonate or barium carbonate from the metallic oxide, and these ferrite magnets are very extensively used now in ceiling fan on the rotor. So in some grades, other chemicals such as cobalt and lithium are also added to improve the magnetic performance. Like, so this ferrite magnet, there are two chemical varieties of ferrite magnet. Barium ferrite is also known two chemical symbols like typically BAF12O19 or BaO6F2O3, and strongest strontium ferrite is known also by two chemicals like SrF12O19 or SR6Fe2O3, and these are the typical the shape of ferrite magnets. Of course, I told these are the brittle and they are made into single piece. I mean, they cannot be eliminated for in structure, so they are used for different applications, different shape. Like, so, and how this is the property typically of different brands of the ferrite magnets are there, the property and the shape. For application where powerful magnets are not required, they are resistance to demagnetization, coercion, and high temperature. and then application are brakes, loudspeaker, motors, and generators. Then we come to rare earth magnets, which comes from the earth, so invented in 1960 and introduced in 1970. And sodium cobalt magnets were the first commercially available rare earth magnet. And they offer excellent temperature stability and high resistance to demagnetization and corrosion. And the cost is only the drawback here. It is a little higher cost. Both sodium and cobalt are relatively expensive elements due to their supply restrictions. And you can just see how the shape of typically of another same cobalt and how the shape of neodymium iron boron are there. Of course, neodymium iron boron are more popular nowadays compared to same cobalt. Same cobalt used of aerospace industries where temperature change over a wide range. Neodymium iron boron start now coming with a good property and use very large number of to reduce the size of the machines and making the machine more efficient and cost effective and lighter weight. So you can just see these different kind of material of sodium cobalt and boron, how they look like with the different composition, material part percentage, and which kind of materials are used in this. And these are the typically the residual flux density, which goes as high as 1.47, and how much is the core shear force, and how much the typically the you can call it the energy density as it goes as high as like at 280. I mean typically kilojoules per meter cube. I mean typically, or it goes to 415 typically in case of neodymium iron boron, as you can see here. I mean invadium like. So application of neodymium magnets are hard disk drive, which are very large volume but typically very important application, and outdoor equipment, dentures, magnetically coupled pumps, motors and generators, MRI machines, and dynamic levitation systems like. Well, semi-cobalt applications are used in applications with wider temperature range, having longer corrosion resistance and superior magnet application, electric vehicle motors, turbo machinery, pump coupling, and high temperature critical applications like, as you can see the photograph of typically of the electric motor. And these are the different grades of neodymium iron boron. I mean coming off from different countries with the different energy density, different cores, typically radial flux density, and you can see the continuous improvement of this maximum BH curve goes. I mean energy density goes as high as 430, typically where it was 83 in or typically in farad. And these are the of course the properties for typically of residual, typically of sodium cobalt magnets like. So these are the founded material. Now coming to electrical conductors, as you can see, we use the electrical conductor for different electrical equipment. Almost every electrical equipment is starting from cable, transformer, rotating machine, or other component like inductor. We use this electrical conductors also. So winding wires or magnet wires are annulled. Wire is a copper or aluminum wire coated with a very thin layer of insulation, and is used in the construction of transformer, inductor, motor, generator, speakers, hard disk, actuator, electromagnet, and electric guitar pickups. And magnets wire insulating film used in order to increasing temperature range for nebular former and prototype formaldehyde. These are the typically different kind of insulating material on which the wires are put. And insulated magnet wires is capable of operating up to 240 degrees Celsius. And aluminum also used as an alternative for large transformers and motors because of its low electrical conductivity. So aluminum wires requires 1.6 times larger cross section area than a copper wire to achieve comparable DC resistance. As you can see the copper wire and aluminum wire, how they look like it relatively. And then the typically classification of the magnet or enamelled winding wire size of conductor measured as per AWG, American wire gauge, or we call it standard wire gauge in millimeter or inches. And thickness of insulation, we call it grade 1, grade 2, grade 3. Higher grades have a higher thickness of insulation, thus higher breakdown voltage. And type of enamel and thermal class, common temperature or absolute temperature is 105 degrees Celsius, 130 degree, 150 degree, 180 degree, and 220 degrees Celsius. So conductors we normally use copper, aluminum, brass, and iron. And insulators we use file bars, support frame, castable compound. And resistivity of different conductor material is typically copper is the lowest, then followed by aluminum and silver, the highest, lowest resistivity, and then followed gold like in between. So you can call it the conductors like AC resistance and DC resistance. So AC resistance is certainly lower, and when you DC resistance is lower, and when you have applied The AC resistance, even at 50 Hz, the AC resistance increases to order of like 10%, 1.1 due to skin and proximity effect. The current trying to flow only in outer surface area. It does not go to dense part of the conductor. So that's also causes typically also responsible for eddy current losses in the conductor due to circulating eddy currents in the conductor. That's the reason this effective AC resistance increases when you apply the AC current through these conductors, like, and it's quite famous. The resistance is also affected by the temperature. I mean, because you have a positive temperature coefficient, that what you have 0 degree Celsius, I mean, if temperature increases, the resistance of the conductor also increases by this relation line. And resistance of copper increases 30% from 20 to 100 degrees Celsius, typical example. And of course, you can see that how different resistivity, temperature coefficient, and conductivity of these different conducting materials, I mean, they are typically in this table from a reference. And then you have a, typically I told you, you have a different wire gauge like American wire gauge or standard wire gauge, British standard wire gauge, which we are taking, or National Electrical Manufacturing Association. They have given different, and international electro type. These are the typical standard. I have given this concept of this wire gauge. So here we have a wire gauge of copper conductor in AWG, means American. You can just see how the wire gauge goes into the typically, and how the typically, I mean, the different sizes typically goes in different conductor sizes. And typically American wire gauge how changes with typically here with the copper, aluminum and copper wires. And then the AWG or standard wire gauge conversion table, I mean, from you convert like in inches to, in both the cases, how it is changed with the gear gauge. First is the wire gauge. Increase with the wire gauge means the reduction of the your cross section area of the conductor. So it goes just like exactly opposite one. Now coming to superconducting material, we have, I mean, there are superconducting machines, but these conductor can be designed with very high value of current density, reducing drastically the size of the machine. And with superconductor, the copper losses are extreme, binding loss are extremely low, and the material, those who resistivity sharply decreases to practically zero value when temperature is brought down below a transition temperature, are called superconductor. And here are the different elements where which are the superconductor and their temperature, I mean, at what temperature below which we have like a superconductors, like also, and maybe compound, they are able to go a little higher temperature rise. And because of this, we have some time chronology, typically a technology which reduces the temperature below a certain level to make these alloy as a superconductor in different machines, like. So these are different applications where superconducting materials are used, I mean, with the proper technology, even like a you can call it SMS, superconducting magnetic energy storage system, fusion reactors, MRI, I mean, different applications like that. Now coming to like insulating materials, we have a different kind of insulating material. The insulation put on the conductors to so that current is confined within the conductor cross section area. So development of insulating material, we have positive features: increased thermal durability, we require increased dielectric strength and increased thermal conductivity. So we have a negative features: more brittle material and increased potential for damages, and may slow down the production rate. So we have a different class of insulation used normally in electrical machines, starting class Y, I mean, or O we also know. So temperature in Celsius is, withstand temperature is 90 degrees Celsius. Class A, the withstand temperature is 105 degrees Celsius. Class E, I mean, temperature withstand capability is 120, and class B 130 degrees Celsius. And class F is 155 degrees Celsius. Class H is 180 degrees Celsius. And then we have a typically the other classes 200 or 220 or 250, where the temperature withstand capability is corresponding to these numbers, like. So these are different class of insulation which changes with the material property. And if you take a better class of insulation, as we can see, we use the class of insulation compared to class B, then we can allow the higher temperature rise. It means the same surface area can dissipate more the losses in the machine. So machine size can be reduced, I mean, to low. I mean, so this becomes very important in the design. However, it uses only very small volume of part of the machine on the conductor, but it really decides the cost and size of the machine, that you can allow the dissipation of more heat, you can produce the more losses and get the more output from the same machine, like. So coming to different classification, the class Y insulation consists of materials such as paper, silk, wood, fiber, cellulose, and similar organic material, neither impregnated nor immersed in oil. And these materials have tendency to absorb moisture and rotate rapidly, and maximum allowable temperature is 90 degrees. Now coming to class A insulation, consists of material, it consists material of the cotton, silk, and paper, and when suitably impregnated or coated, or when emerge in a dielectric liquid such as oil. Another material or combination of material may be included in the glass. In this class, if by experience or test they can be shown to be capable of operation at the class A temperature. I mean, and the maximum allowable temperature is typically 105 degrees Celsius or 221 Fahrenheit. Like I normally use these in paper insulation in transformer. Then the class insulation consists of enameled wire on base on formal epoxy and resins on molding powder, plastic or funnel, etc. And you can see how it looks like. They can withstand 100 degrees Celsius temperature or 240 degree Fahrenheit, and they are used in 3M Scotch Super or brown bakelite rods, or they use brown bakelite. Then class B insulation consists of materials of combination of materials such as mica, glass, fiber, asbestos, etc. with suitable bonding, magnetic or coating substances. If you older application use asbestos, the maximum allowable temperature is 100 degree, 130 degrees Celsius or 260 Fahrenheit, and they are normally used adhesive powder, polyester film tape, or epoxy glass tube, or mica insulation sheets. The class of insulation which are very common nowadays consist of materials of combination of materials such as mica, glass, fiber, asbestos with suitable bonding, magnetic or coating substance, as well as the other material of combination of material, not necessarily inorganic, which can be by experience or test can be shown to capable of operation of class F temperature at 25 degree higher than B, and it's a one maximum withstand temperature is 155 degrees Celsius or 311 Fahrenheit, and normally use the fiberglass sheets like. So class H insulation, it consists of materials such as silicone, elaster, and combination of materials such as mica, glass, fiber, asbestos with suitable bonding, pigmented or coating substances such as appropriate silicon resin, and maximum withstand temperature capability 180 degrees Celsius or 300 Fahrenheit, and silicon resin impregnated with high temperature mica insulation, as you can see in the photograph. Now coming to class C insulation, contains ceramic, quartz, asbestos, glass and mica, which are neither impregnated nor bounded with organic substance, and maximum withstand temperature capability is 180 degrees Celsius or 311 Fahrenheit. Like now coming to standard and standardization in these electrical machines. So we have a different standard called typically International Standard IEC, International Electrotechnical Commission, which is called IEC, and of course they have a regional standards like CENELEC, like European Committee for Electrotechnical Standards, or NEMA, National Electrical Manufacturing Association, or we have NSI, American National Standards, and IEEE from typically Institute of Electrical Electronics Engineers in US, and we have National Industrial VD in Germany, SFS in Finland, SEN in Sweden, and DIN in Germany, and BS in Great Britain, and India, of course, we have a BIS, Bureau of Indian Standards. Now these are the different standards coming from IEEE for design of these electric motors. As you can see, the big list for different rating motors, starting typically from 370 kilowatt motors and go to typically the motors of different class of around. If you look into category class 1E and all that, so similarly totally closed, or you can call it like a typically different kind of motors, generators. So it's a big issue, and these are the IEC standard. For different parts of the rotating machines standards. Again, a set of IEC standard for adjustable speed drive. Different kind of machines used for different applications like. And then list of British standard, BSA standard. Used for typically synchronous motor or different applications machines like for even traction or other applications. And these are the big list of British standards. Also. Now coming to standard definitions and classification. So classification according to the motor sizes, we classified these different electrical machines according to the size. A machine is an electrical apparatus which depends on electromagnetic induction for its operation and which has one or more component members capable of rotating movement. And we have a small machines, we call it fractional horsepower, fractional kilowatt motor is built frame size. Then that of medium machine has a continuous rating of 1700 to 1800 RPM of 1 HP motors or 0.575 kilowatt generator, and motor of less than 1/3 horsepower or less than 800 RPM. So we have a medium or integral horsepower machines, DC machine with a continuous rating of 1.2 or so to 1 kilowatt, and AC machines of course different speed and different horsepower with a different kilowatt and power factor. Large machine like a DC machine of continuous rating of 1.2 to 1 kilowatt, or AC machines even for more than 450 RPM. So coming to another classification according to type of motors, we have a DC motors and its type, and induction machine type, and synchronous motor in types, and you can see the 3 photographs of different machines like. Then coming to classification according to the class, so we have a, even in the case of induction motor, we have a many polyphase squirrel cage induction motors are available in market, meet the demand for several industrial application and various starting and running conditions required. They are classified according to the class as class A, class B, class C, and class D, having a different starting torque and different full load speed corresponding. Then of course, typically how they differ it depends on the typically rotor bar construction. The class A motors, how it look like, which require a high starting current and low running slip, so that efficiency is high, used in fan and compression. Class B motors, they are used, typically have a high starting torque and with low leakage reactance, so that overload typical capacity accordingly modified. Then class C, what kind of double cage bar construction used with high starting torque, used compressor, conveyor, reciprocating pump. And class D with again double cage used in punch presses, high machines with a high starting torque also. So now coming to standardization, so we have a different voltage standard like 220 40 for single phase, 340 380 to 415 for three phase, and again 500 volt and 660 690 used for different applications. As you can see table here is NSI 380.1 for different motors nameplate, different standard. As you can see the same nameplate, as you can say 400 690 50 horsepower or 22 kilowatt, and 50 or 22 kilowatt and 60 or 220 kilowatt model. Then these are the typically nameplate reading. As you can see the different parts here, the frequency, phase, duty, speed, horsepower, volts, uh, typically amperes, the different codes, then the frame size and duty, and even typically efficiency are also given. And these are the typical technical specification at glance for IC based squirrel cage induction motor. As you can see the different parameters of it as a technical specification for. Then you have nominal tolerances on these standard, that how much tolerance, like voltage deviation permitted plus minus 5%. Like Indian conditions, like in we allow plus minus 6% voltage variation, but if we go to typically in rural areas, we allow plus 6% and minus 16%. So these are depends on application how we really permit the different typically standard tolerances. Like now coming to efficiency standard, this has become very important probably in last one decade, when we have really the efficiency very marked according to IC standard. We have I1 standard efficiency, then high efficiency I2, and I3 premium efficiency, and I4 super premium efficiency. You can say by 2015 all motors between 7.5 to 7 are sold in European Union as called I3. So you can just see how the efficiency typically in different power motors, normally for the induction motor, 4 pole squirrel cage induction motor, how this efficiency curve are there. You can say I4 is the higher efficiency, and the difference is efficiency is also substantially, as you can see. And if you look into lowest I3, it's a 92, typically 94%, and where it goes to 97% for I4, even for rating of 375 kilowatt. But this margin is really very large if you really talk about, the motors of typically of 0.75 kilowatt of order of 1 horsepower or 2 horsepower. So coming to degree of protection standard, so there are different protection standards also, like we call it a typical standard called IP6. The first number is the typically particle person, the motor protector against the solid object greater than 12 millimeter, and motor protected against the solid object of 1 millimeter, dust protected motor, dust tight motor. Similarly, second number represent water ingress protection, motor protected against the spraying water, motor against protected against Spanish water, motor protected against water jets, motor protected against the heavy sea. And this is the impact for typically ingress protection, index of protection classes of different IC 16. These are the standard how really a protection class varies for. Now coming to cooling standards, there are different cooling standards also in these rotating machine, especially electrical machine. So these are how it is really height and what is the meaning, or typically as you can see the nomenclature for IC standard for the purpose of cooling standard, like different kind of cooling. and whether it is a typically a self-cooling or it's a typically force cooling or it is a really some liquid cooling. We use in different rating machines also. So these standard different digit talk about 4 different type of cooling, whether it is a free cooling, self-calculation, machine mounted independent component for cooling also. Now coming to enclosure standard, these are also very important because you should be able to replace the motor from any manufacturer for particular size and location. So we have here the NEMA standard. As you can see, the outside typically the body how it goes. With the NEMA, develop a set of standards related to electric motor that include design classes, frame size, and enclosure. And NEMA designates a certain enclosure of motor divides into 2 categories: open machine and totally closed machine. And typically, example is double open drift motors allow airflow and have internal fans to assist in maintaining air movement to help keep motor cool. And the enclosure around these motors have ventilator opening that prevent liquid and solid from making their way the angle between 0 to 15 degree, and typically used in indoor application relatively clean dry location. Then you have totally enclosed fan cooled called TLFC, prevent the free exchange of air between the inside and outside of the frame, but does not make the frame completely airtight. A fan is attached to the shaft of the pushes the air over frame during the operating to help the cooling. And used on pump, fan compressor, industrial bed drive, and direct connected equipment. Then you have a totally enclosed, non-ventilated motors, so TENV, so TFC, but has no cooling fan and relies on convention of for only convention for cooling and no vent opening, tightly enclosed, prevent from free exchange of air, but not airtight. These are suitable use for which are exposed to dirt, dampness, but not much hazardous explosion. Totally enclosed air cooled. Typically you can see how the motor looks like. So dust tight fan and blower duty motors designed for shaft mounted fans and belt driven fans, and the motor must be mounted within the airflow or fan. Now totally enclosed wash down motor, as you can see in the photograph, so designed to withstand high pressure wash down for a high humidity wet environment, available in TO, TFC and TNV enclosure, totally enclosed hostile for severe environment, and designed to use extremely moist or chemical environment but not hazardous location like food processing, packaging, pharmaceutical application where motor are regularly exposed to high pressure wash down. Then explosion proof enclosure EXPL, as you can see the motor how look like. The explosion proof motor is totally enclosed machine and is designed to withstand an explosion of a specific gas or vapor inside the motor casing and prevent ignition outside the motor by spark, flashing or explosion. These motors are designed for specific hazardous purpose such as atmosphere containing gases or residual dust. For same operation, maximum motor operating temperature must be below the ignition temperature surrounding glass or vapor such as chemical plant, oil industry or gas work, and wood and plastic processing industry or in agriculture. So now coming to mounting arrangement standards. So we have a different kind of mounting or code, from which the different frame are there, because you should be able to these are the different standards so that the motor can of different manufacturer can fix on the same location. So they are numbered for different kind of their dimensions, like as you can see the kind of then vibration rating standard. What is the level of vibration? Because that produces the noise, whether you have it normal or reduced vibration or spatial vibration. And then typically the class of, we already talked about the class of insulation material. So these are the different class of insulation used for different thing of the motor. Now we have some of the problems, so typically solved problem. Coming to that, the question is what is the direction of magnetic lines on force? Answer is magnetic lines are the north pole to south pole outside the material and south pole to north pole inside the material. Question 2 is what is the unit of magnetic flux density? It's magnetic flux density, answer is Tesla. Question 3, what is the reluctance of air gap as compared to the iron or steel? Answer is air gap has large reluctance as compared to the steel or iron. Question 4, what is the magnetic field is slightly repelled by a magnetic field? Answer is diamagnetic material. So question 5 is explain Fleming right hand rule. The answer is Fleming right rule states if we arrange our thumb, forefinger and middle finger of the right perpendicular to each other and the thumb finger towards the direction of the motion of the conductor related with the magnetic field, and the forefinger points towards the direction of the magnetic field and the middle finger points towards the direction of induced current as shown in the figure. Then question 6 is what is the retentivity of the material? The answer is the tendency of magnetic material to maintain magnetism even in the absence of magnetic field is known the retentivity or remanence. And question 7, what is the coercivity of material? The answer is the magnetic field strength H required to demagnetize the magnetic material is known as coerciveness or coercive force. So question 8 is the compare the soft and magnetic material. So here is the comparison, like soft material have a low hysteresis loss, low domain wall relativity, low coercivity, and can be easily demagnetized and magnetized steel. Hard material have a large hysteresis loss and domain wall mounted difficult, coercive force and very large, cannot easily demagnetize or magnetize, and magnetic strength can be large. They are used, hard magnetic material used as a paramagnet, soft material paramagnetic material used as a core of different magnet. Question 9, list the ferromagnetic material used in motor. So answer is low carbon steel, silicon and copper alloy of different kind are used in this. And typically question 10, which rule is used in electric motors and generator? Answer is Fleming left hand rule is in motors and Fleming right rule is used in electric generator. So now there are some numerical problems typically. So question 1 is determine the flux density when magnetic flux is 9 microweber and cross section area of magnetic field is 5 into 10 power minus 3 meter square. So we have a solution as pi equal to 9 microweber, area is 5 into 10 power minus 3 meter square. So flux density is pi upon A, and that comes 1.8 millitesla. Question 2 is calculate the magnetic field at the center of a square loop which carries a current of 1.5 ampere. Length of loop is 50 centimeter. So I is 15 ampere and length is 0.5 meter, and we have to calculate the flux density. So flux density is 2 root 2 mu 0 I upon pi L. So keeping the value, we get the flux density of 3.4 into 10 power minus 6 Tesla. Now question 3, two materials X and Y are magnetized whose intensity of magnetism are 500 ampere per meter square and 2000 ampere per meter square respectively. If the magnetizing field is 1000 ampere per meter, then which among the two materials can be easily magnetized? So taking M equal to 5 ampere per meter square, M by 2000 meter and H equal to 1000 meter square, so we can find out X. It comes for the X material, it comes 0.5 and Y material it comes 2. So susceptibility of material Y is greater than the material X. So material Y can be easily magnetized than X. The question 4 is what is the flux density of neodymium iron magnet? The answer for neodymium iron magnet has a flux density of 1 to 1.4 Tesla, and so sinter material have a flux density of 1 to 1.4 Tesla, and bonded neodymium have a 0.6 to 0.7 Tesla. Question 5 is the magnetic field shown in the figure is due to the current carrying wire in the direction that the current flows. So using the right hand rule, the current flows in upward direction. The question 6, compute the magnitude of the magnetic field of a long straight wire carrying conductor of 1 ampere at a distance of 1 meter from it, comparative with the magnetic field distance. The solution is given that I equal to 1 and R equal to 1. So B straight line mu 0 I upon 2 pi R. So it comes around 2 into 10 power minus 7 Tesla, where the earth magnet have a 10 power minus 5 Tesla. So B straight is the 100 times the smaller than B earth. Question 7 is calculate the strength of magnetic field at a distance of 20 centimeter from pole strength of 40 ampere meter in air to find the induction in the same point. So solution is the strength of magnetic field due to the pole strength of M is given M is 40 ampere per meter and 20 then. So H equal to M upon 4 pi square. So it comes 70.57 ampere per meter. Now magnetic field induction at the same point will be flux density. If we calculate mu 0, it comes 10 to power minus 4 Weber per meter square for Tesla. So question is a paramagnetic material has a 10 to the power 8 atoms per meter cube. Its magnetic susceptibility at temperature 350 is 2.8 into 10 to the power 4. Calculate the susceptibility at 300 degree Kelvin. The solution for paramagnetic material, the susceptibility is inversely proportional to 1 upon T. So we can just calculate, it comes X2 comes 3.26 into 10 to the power minus 4. Question 9 is a solenoid of 0.5 meter, has a radius of 1 centimeter and made of 500 tons. It carries a current of 5 ampere. What is the magnitude of magnetic field inside the solenoid? The number of tons per unit length is n equal to 500 upon 5, so it's 1000 tons per meter, and L equal to 0.5 meter, radius is 0.01 meter. Thus L upon A is 50. So L is much greater than, hence we can use the long solenoid formula to be equal to mu 0 Ni, that it comes around 6.28 10 to the power minus 3 Tesla. Question 10 is what is the magnitude of direction of magnetic field at point P. So we can, where current I equal to 15 and the distance 1 centimeter. So B is mu 0 I upon 2 pi r. So we can calculate it comes around 0.3 millitesla. The question is, what is the force of per unit length of two conductor carrying conductor of 5 ampere separated by distance of 20 centimeter in the air? The force per unit length of two conductor is given F equal to mu 0 I1 upon I2 into 2 pi d. That comes 25 into 10 power minus 6 Newton. The question 12 is, find the maximum force on the conductor having a length of 6 centimeter, current 2.75 ampere and flux density of 0.9 Weber per meter square. The force on conductor F BIL sin theta beta equal to 3.75. All that, so getting a force equal to PIL, it comes 14.85 Newton. So there are unsolved problem which you can do yourself. I mean, there is a answer is given, and typically these are the some of the textbook and references which is referred for preparing this lecture. And thank you very much. Thank you.